Bismillah ar-Rahman ar-Rahim. Today we will talk about Chapter 2, Lecture 2. In Lecture 2, we will discuss the electromotive force and the circuits. Then we will discuss the energy and the power in the electric circuit. Let's start by the first slide. Why we need a closed loop circuit. So, if we have an electric field E1, this electric field produced inside an insulated conductor causes a current, of course. Because as you know in the previous lecture, we have the current density is equal sigma multiplied by the electric field. So if we have an electric field inside this conductor, we have a current. Good. Then the current causes charge to build up at the ends. Of course, the charges, the positive charge will move with the direction of the electric field and the negative charge opposite to the electric field because the force is equal QE. If the charge is positive, so they will be built up at with the direction of the electric field, and if they are negative, so they will be in the other side because the force in this case will be opposite to the electric field. So we see here that we have a new electric field. The charge built up produces an opposite electric field E2, thus reducing the current. After a short time, E2 will be equal to E1 in magnitude. So they will have the same magnitude. And in this case, the total electric field will be 0. So no electric field, no current density, no current. So in this case, we can say that the current is 0. So for that, we need a closed circuit. You have probably already thought water does not flow through a pipe without a pump. So to make the water flow up, we need a water pump. The same thing for the circuits. To make the charge moving through the circuit, we need a pump. This pump will be an electric potential difference. In an electric circuit, there must be a device that acts like a water pump. The direction of the current in such device is from the low potential to the high potential. Such device is called a source of electromotive force, EMF. Example, battery, electric generator, and solar cells. So on the electric circuit, we must have a device acting like a water pump in the fountain, for example, that pump the charges in the circuit. This source converts energy from some sources into electric potential energy. So for example, if we take the battery, it will convert the energy from chemical energy to electrical energy and transfer it into the circuit. The influence that makes the current flow is called electromotive force and denoted by epsilon. In spite of the name, it's not a force, but it's a potential difference. Its unit is 1 volt, and volt is equivalent to joule divided by a coulomb. So it's okay. So what do we call this epsilon? Epsilon is called electromotive force. Good. A constant current can be maintained in closed circuits through the use of sources of energy called electromotive force. Electromotive force sources can be battery and can be generator. And they are acting, as we said, charge pump. Let's move. As you know, we have two different types of battery. The first one is ideal battery. In the ideal battery, we don't have any internal resistance. The internal resistance is denoted by small r. In this case, is equal to 0. We consider the circuit shown below consisting of a battery of electromotive force epsilon and connected to an external resistance capital R. As we said, small r, the internal resistance is null, 0. In this case, what is the potential difference across the resistor? The potential difference across the resistor can be given by Ohm's law, Ri. And since the resistor is connected parallel to the potential difference, parallel to the electromotive force source, to the battery, in this case, we can say that epsilon equal Ri. So what is the current in this case, in this circuit? The current is epsilon over R. And we are done with the first part. It's okay. Good. Let's continue. Now we take the case of real battery. A battery has an internal resistance R different to the zero. So the battery in this case is denoted by, the battery in this case is symbolized by the battery, a potential difference, epsilon, and an internal resistance, small r. This is our battery. Okay, so the battery has an electromotive force, epsilon, and has an internal resistance. The real source of electromotive force actually contains some internal resistance R different to the zero. The terminal voltage of electromotive force source is VBA. How much? It's epsilon minus Ri. If an external circuit containing a resistor R, external resistance, connected across the source of the terminals A and B, we have, according to Ohm's law, delta V in this case is also Ri. And this resistor is connected parallel to the battery. So it's equal from the other side, epsilon minus Ri. So what will be epsilon in this case? What will be the current in this case? The current in this case would be epsilon divided by external resistance or load resistor plus internal resistance. The current is equal to the electromotive force, the electromotive force divided by the total circuit resistance. Okay, so we have to differentiate between the ideal battery and the real battery. In the ideal battery, I equal epsilon over R. In the real battery, I equal epsilon over R plus R, internal plus external. And we introduce here the different symbols of the circuit diagram. For the wire, conducting wire with negligible resistance is symbolized with a line. This is the symbol of resistance. This is the symbol of source of electromotive force. The longer vertical line represents the positive, while the short terminal line represents the negative side. The potential difference is from the negative to the positive side. Okay, if we have, for example, in this case, for the real battery, we have a resistance, internal resistance, and we have an electromotive force, epsilon, and this is I. Okay, the voltmeter and the ohmmeter are symbolized by the circle with the V or A inside. We take an example 25.4, the source in an open circuit. The figure shows a source, that means a battery, with electromotive force 12 volt and internal resistance 2 ohm. So here we are talking about real or ideal battery. Of course, it's a real battery. Why? Because a small r is different to the zero, it's equal to ohm. The wire to the left of A and to the right of the ohmmeter A are not connected to anything. So it's an open circuit, as we said in the title, it's an open circuit. Determine the reading of the idealized voltmeter and ohmmeter. Let's start by the ohmmeter. For the ohmmeter, open circuit. So as a result, no current, I equals 0. When we have an open circuit, that means I equals 0. Let's discuss now the voltmeter. We have a real battery. I equal, we have a real battery. So VAB equal what? The potential difference from B to A is equal epsilon minus Ri. However, this I is equal 0. So it's only epsilon. So it's 12 volt. We are done. So the voltmeter will read 12 volt. Let's take this example. Using the battery in the previous example, we add now 4 ohm resistors to form a complete circuit and a closed circuit. Closed circuit. In this case, what will be the reading of the ohmmeter and the voltmeter? Let's start by the ohmmeter. I equal epsilon over R plus small r. because we have a real battery connected in parallel with the external resistance. So it would be epsilon is 12 divided by capital R external resistance 4 plus 2. So it's 2 ampere. Now let's discuss the reading of the voltmeter. The voltmeter will read the following: potential difference from A to B, so that means VAB equal epsilon minus Ri. Epsilon how much? It's 12. R is 2 multiplied by the current is 2. 12 minus 4, so the voltmeter will read the 8 volt. We are done. Let's take this example. The voltmeter and the ohmmeter in the previous examples are moved to different positions in the circuit. What are the voltmeter and the ohmmeter reading in the following situations? So now you see that the voltmeter is connected across the resistor. And the ohmmeter is at the same position. So what will be here the current? We have a real battery and we have external resistance. So we have the current is epsilon plus capital R plus small r over capital R plus small r. So it would be 12 divided by 4 plus 2. So we have again 2 ampere. This is the reading for ohmmeter. What about the voltmeter in this case? The voltmeter is connected across the resistor. So across the resistor, delta V, or let's write V A prime A is equal R multiplied by I. Here we are talking about Ohm's law across the potential difference across the external resistance. So it will be R is 4 multiplied by the current is 2, so it's 8 volt. Let's move to the second circuit. In the second circuit, the voltmeter is connected series. However, the voltmeter has very high internal resistance. So what happened to the current? The current will be blocked here, and the current in the circuit will be 0 because the voltmeter is connected in series with its high internal resistance. So the current is 0. What about the potential difference now? The voltmeter is connected from here to here. Okay? So there is no current here, so that means delta V equals 0. There is no current here, that means delta V equals 0. And here we have only epsilon. So the reading of the voltmeter, V BB prime equal only epsilon, because no current in the circuit, so we have only the potential difference across the battery. That means the electromotive force, which is equal to 12 volt. And we can say here that the voltmeter measures the potential difference VB prime between the point B and the point B prime. Since the current is 0, the potential difference across the resistor is 0. And the potential difference between the ends of AA prime of the idealized ohmmeter is also 0. And so VB prime is equal to VAB, the terminal voltage of the source. As a consequence, we can get no current in the circuit, so the terminal voltage equal to the electromotive force of the voltmeter reading, and the voltmeter reading will be 12, as we said. Okay, so what we can say that there is no current through the idealized voltmeter because it has an infinitely large resistance. So the resistance, the internal resistance of the voltmeter is very large. And the current in this case will be 0. No flow of the current. Using the same battery in the preceding example, we now replace the volt-ohm resistor with a 0 resistor conductor. What are the reading of the voltmeter and the reading of the ohmmeter? We don't have any external resistance, so that means the terminals of the battery are connected together. Okay? A is connected to B. The voltmeter has no internal resistance, very small, so it will not be considered. So in this case, we are connecting like that. Okay? So what we're gonna get? What is the reading of the ohmmeter? ammeter in this case is equal, the current in this case is equal epsilon over R plus R, but we don't have this R, so it's epsilon over R, internal resistance. So it will be 12 divided by 2. So in this case, we have 6 ampere in the circuit. What about the reading of the voltmeter? The voltmeter is connected across the battery. So that means VAB equal epsilon minus RI. So it will be 12 minus internal resistance 2, current is 6. 12 minus 12 is 0. In this case, we can say that our circuit is, the situation here is called short circuit. The external circuit resistance is 0 because terminals of the battery are connected directly to each other. The short circuit current is equal to the electromotive force divided by the internal resistance. Okay, so this is the short circuit, is the potential, the electromotive force of the battery divided by the internal resistance, and we are done. Okay, now we want to move to the power. The net charge in the potential must be 0 for the round trip in the circuit. And we can say that epsilon, the electromotive force, minus Ri, so here we have a drop of the potential, minus IR, the external resistance, and the total will be equal 0. The potential rise electromotive force and drops in the resistors. Okay, what about the power now? The power input or power output in the electric circuit. Power input to a pure resistor. If the circuit element is a resistor, in this case, the potential difference will be IR based on Ohm's law. And then the power delivered to the resistor will be the potential difference multiplied by the current, or I squared multiplied by the resistance, or potential difference squared divided by the resistance. All resistors have power rating. The maximum power the device can dissipate without becoming damaged. So for the resistors, this is the power. VI, I squared R, or V squared R. What about the power output from the source? The rate at which the source delivers energy to the circuit is equal V multiplied by I. But we know that V equal VAB epsilon minus RI. So that means we can get the power equal epsilon I minus I squared R. This term is called the rate at which work is done on the circulating charge, or it's called the power conversion rate, the energy conversion rate. And this term is called the rate at which the electrical energy is dissipated by the internal resistance, or it's called the energy delivered to the internal resistance or dissipated by the internal resistance. So it's, for a pure resistance, the resistance is always consuming the electric power. Resistance convert the electric energy to another type of energy like the light, the heat, or mechanical energy. What about the electromotive force source? If the current passes through the electromotive force from the negative side, that means the low potential, to the positive side, that means the high potential, the electromotive force source produces electric power. In this example, the current is entering the negative side of the battery and leaving the positive side of the battery. In this case, it's producing. What is producing? Produces an electric power. On the opposite side, the current is entering the positive side of the battery and leaving the negative side. In this case, is consuming. So the battery can be producing energy or consuming energy. It's okay. So I repeat, if the current is going from the positive to the negative, in this case is producing. If the current is going from the negative to the positive, in this case is producing, is consuming, sorry. Find the rate of energy conversion. Rate of energy conversion is the power. Okay, chemical to electrical. That means we are talking about epsilon I. This is the rate of energy conversion. And the rate of dissipation of energy in the battery and the net power output of the battery. Let's try to do this example step by step. Okay, rate of energy conversion. Epsilon I. Epsilon I in our case, epsilon is 12 and I is 2. So it's 12 multiplied by 2. So it's 24 watts, the unit of the power. Okay, next, he's asking about the rate of dissipation of energy in the battery. Rate of dissipation of energy in the battery. In this case, power dissipated in the internal resistance, it will be I squared multiplied by small r. So it's equivalent to I is 2 and R's internal resistance is 2 also. So I squared R. So it's 2 squared 4 multiplied by 2 is 8 watts. Good. Third question, he said the net power output of the battery. Power output. So the power delivered to the circuit or delivered to the circuit. What will be the power output? It will be epsilon I minus the energy dissipated, the power dissipated in the internal resistance. So it's equivalent to 24 minus 8. 24 minus 8 is 16 watts. So 16 watt is delivered to the circuit. So if I ask another question, what is the power delivered or dissipated by the external resistance? It will be 16. Good, we are done. Let's take another question. A battery has an electromotive force epsilon equal 12 and the internal resistance R equal 0.05 ohm. The terminals are connected to the load resistance equal 3 ohm. Find the current in the circuit. Here we have a real battery connected with an external or load resistor. Very good. Okay, we take an example. What is it? Good. Let's do it step by step. The question said, what can I find the current? What about the current? I equal epsilon over capital R plus small r. So it will be epsilon is 12 divided by 3 plus 0.05. So the result is 12 divided by 3, 3.934. 3.934 ampere. Very good. We are done with the first question. Here we have a battery connected with a real battery. Connected to an external resistance, capital. Find the power delivered to the load resistor. Power delivered to the load resistor. Yeah, the power delivered to the load resistor. What do we have? Good. Power delivered to the load resistor. That means I squared multiplied by capital R. So it will be the current is 3.934 power 2 and the external resistance is 3. We are done. How much the result? The result will be 46.43. 46 0.43 watts. The power delivered to the internal resistance, the same thing, it will be I squared multiplied by small r. So it will be 3.934 power 2 multiplied by 0.05. So the result is 0.774 and 0.774 watts. Okay, what is the power converted by the battery? The power converted by the battery. What will be the power converted by the battery? Power conversion equal epsilon I. So it's equal, epsilon is 12 multiplied by 3.934. That's right. We are done. So this is how much? 47.2. The second method, power conversion, is the total power delivered to the circuit. Is the power delivered to the circuit, to each element of the circuit. So it will be power dissipated by the internal resistance plus power dissipated by the external resistance, and we will get again 47.2 watt. We are done. Let's take another example. Show that the maximum power delivered to the load resistor in the figure occurs when the load resistance matches the internal resistance, that is, when R equal small r. The question said, what is the power, at which condition the maximum power is delivered to the circuit? The condition said, when we have capital R is equal to small r. The internal resistance is equal to the external resistance. It's okay. In this case, we can say that we have the maximum power delivered to the circuit. And we can follow the same steps here. As you know, the power is I squared multiplied by R, and we have a real battery connected to load resistance, so that I will be epsilon divided by R plus capital R, and I squared will be epsilon squared divided by R plus capital R squared, and the power is I squared multiplied by R, so we will multiply this quantity by R, and then to get the maximum, that means the derivative is 0 with respect to capital R. If we derivate this equation, we get a polynomial equation equals 0. This polynomial equation equals 0 when we have only capital R equal small r. So when we have an external resistance equal to the internal resistance, in this case, we have a maximum power delivered to the circuit. We take some examples. The same potential difference is applied to two light bulbs. The two light bulbs have the same delta V. Okay, which one of the following statement is true? The 30-watt bulb carries greater current and has higher resistance. What is the difference between the two light bulbs? The power of the first one is 30, the power of the second one is 60 watts. This is the difference. As you know, the power is what? It's I squared R, but here we don't have any information about the current and about the resistance, but we have information about delta V. Delta V squared over R, or it's equal delta V multiplied by I. Let's check the propositions. The 30-watt light bulb carries a greater current. So here he's talking about the current, and he's talking about the resistance. So which one we will use? We will use this equation, because the question, the propositions, there is no information about the current. Okay, so we will talk about this. So we will say that the power equal delta V squared over R. Good. And it's equal in the same time I squared R, because we have also to discuss the current. Delta V is the same. Sorry, we will discuss also the current, so we will use the delta V I. Delta V is the same, so we don't have any problem about delta V. Higher power, 60 power means what? Means less resistance. P2 higher than P1 means R2 less than R1 based on this formula, because delta V squared over R. Okay? To get higher power, that means we need smaller resistance. The same, to get higher power, that means we need higher current. So that means I2 is greater than I1. We are done. The 30 watt bulb carries a greater current? No, it has a smaller current because P2 is smaller than P1. 30 watt bulb carries a greater current? No. Has higher resistance? Yes, has higher resistance. And 60 watt carries the greater current? Yes, I2 is greater than I1. 60 watt carries greater current? Yes. And has higher resistance? No, has less resistance. We are done. Let's talk about this example. For the two light bulbs shown in the figure, choose which rank the current value at the point from the greatest to the least. Okay, we have 3 points. We have many points actually. The current delivered by this battery. The current delivered by this battery. So we have only one battery, so this battery for sure must deliver the current. So the current is going from the positive to the negative side of the battery because it's producing. Okay, in this case, what happened to the current at this point? The current at this point will be split out in two currents. Let's write this is I2, let's write this is I3, and let's write this is I1. So I1 will be equal I2 plus I3. Good. In this case, which one has higher power? P here, let's write this is P2 as before, and this is P1. P2 is higher than P1. And what did we said? We said that P2 equal delta V multiplied by I. Delta V multiplied by I. We have the same potential difference. Why? Because they are parallel. Parallel. So same delta V, which is equal, same delta V, yes. Same delta, which is equal to epsilon. Okay, let's write it epsilon. So same delta V, but the current is not the same. Which one has higher power? The 60 watt has higher power, that means has higher current. So the current I2 at the point C is highest than the point E. Okay? From the greatest is where? The greatest of the point A, because this is the original current, their sum. So point A is greater than point C, and the point C is greater than the point E, and the correct answer is equal. Let's discuss the second example. Okay, an electric heater is constructed by applying a potential difference of 120 volt to a 9 ohm wire that has a total resistance of 8 ohm. Find the current carried by the wire. What is the current carried by the wire? As you know, here we have potential difference, and we have potential difference delta V, and we have resistance R. So I will be for sure delta V over R, and that's all. Delta V is 120, R is 8. 120 divided by 8 is 15 ampere. So we need 15 ampere in this example. Find the power rating of the heater. What is the power of the heater? Power is delta V multiplied by I, which is equal delta V squared over R, which is equal I squared R. Which equation that we will use? We choose this. Why? Because it's as a function of the given in the question. Delta V is 120, R is 8. Sometimes the students, they make mistakes in the calculation of I, so for that we avoid using I, because in the question is given delta V and R. So we are done. So we can write also 120 squared divided by 8. And we will get the same result, 1,800 watts. Let's continue. The last example of this lecture, estimate the cost of cooking a turkey for 4 hours. 4 hours is a time. In an oven, operates at a current 20 ampere and the potential difference 240 volt. The energy is purchased at 0.15 dirham per kilowatt hour. The question is, what is the cost of cooking? The cost of the cooking is the energy multiplied by the cost of 1 kilowatt hour. Here we are talking about the cost of 1 kilowatt hour, so the energy must be expressed in kilowatt hour. And the energy is what? The energy is power multiplied by time. This is the energy. To get the cost, we multiply it by the cost of 1 kilowatt hour. The time must be in hour, the power must be in kilowatt. So we got the result. What is the power here? What do we have as given? We have a potential difference and we have a current. So it will be delta V multiplied by the current, multiplied by the time, multiplied by the cost of 1 kilowatt hour. So we're going to get 240 multiplied by 20, multiplied by 4 hours, multiplied by 0, the cost of 1 kilowatt hour, 0.15 dirhams. Okay, so what we're going to get? 240 multiplied by 20, how much? 240 multiplied by 120 will be 1,000, will be 19.2 times 10 power 3 watts. Okay, all of this. So it will be 19.2 kilowatt hour. Kilowatt hour multiplied by 0.15. So the result will be, what will be the result? Will be 2.8 dirhams. So it will be 2.8 dirhams. It's okay. So we are done. So this is the cost of cooking a turkey. Let's take the class activities. In this example, in this circuit shown, the two light bulbs A and B are identical. Compared to the light A, the light B glows more brightly, less, same, or not enough information in the question. They are identical. Identical, so that means, and they are connected in series. So that means they have the same current. And they are identical, that means R equal R1, RA equal RB. And they have the same current, so that means they have the same power. For that, they will light bulb B glows just as brightly the light bulb A, so they have the same brightness. Here, why? Because they are identical. Same current, same I. Okay, because they are series. And the power is, as you know, I squared R. Same I, same R, that means same power. Good. And the circuit shown in A, the two light bulbs are identical. They have the same resistance. The bulb B has been removed in the circuit, and the complete circuit is shown in the figure B. Compared to the brightness of A, what happened to the light bulb of A? So here, if we remove this, that means we will cancel the resistance. What happened to the total resistance here is decreasing. It will be RA plus RB because they are series. In this case, R equivalent is decreasing. When R is decreasing, what happened to the power? The power is increasing because it's I squared are equivalent. Okay, or we can say the power will increase, so that means the light bulb A brighter. We are done. Thank you so much. See you in chapter 26.